Alright, so we begin the third lecture today. What is the title of the chapter? The title of the chapter is Power Series. The title of the chapter is Power Series, and under this chapter there are several subtitles. So first we shall make a brief review of the theory of convergence of series, and then we will have power series, radius of convergence of power series, examples, use of root test and ratio test, differentiation and multiplication of power series, entire functions, the theorems of Picard and Liouville, and then we will look at special functions like the exponential function, the trigonometric function, Abel's limit theorem, and a lot of exercises will conclude, and then we will conclude the chapter. Okay, so this is the outline of chapter 3. All right. So let us make a beginning with this. So let us review the theory of convergence. So let us begin with the definition of an infinite series. So what is an infinite series? So given a sequence an of complex numbers, an infinite series a1 plus a2 plus a3 plus etc. is by definition limit as n tends to infinity summation k from 1 to n ak, right. So what you do is that you sum the first n terms and the expression Sn, the sum to n terms, let us call it Sn, you calculate the limit of Sn as n tends to infinity, right. If the limit exists, then that limit is by definition the sum of the infinite series. So how do you sum infinitely many terms? You have to sum finitely many terms and then pass to a limit. Now how do you sum finitely many terms? It has to be done in a certain way. You cannot just start taking all possible finite sums, that is not allowed. You are supposed to take the first term, first two terms, first three terms, first four terms, and in that order. So you take the sum to n terms, the first n terms, and that's a finite sum. You calculate that finite sum, you produce a new sequence, right, a1, a1 plus a2, a1 plus a2 plus a3, etc. The limit of this will be the sum of the infinite series. This is a definition of a infinite series, right. All right. Now by way of examples, let me give you the simplest example is that of a geometric series. Geometric series is a plus ar squared, etc. So you sum the first n terms, you can actually sum the first n terms in closed form. This is one of the few cases where you can get this closed form expression for the sum to n terms. So you calculate the sum to n terms, a into 1 minus r to the power n upon 1 minus r, that's, and then you have to pass to the limit. You have to first sum to n terms and then you have to pass to the limit as n tends to infinity. So what is the limit of this as n tends to infinity? A by 1 minus r, because r to the power n goes to 0 as n tends to infinity, r to the power n goes to 0 as n tends to infinity when r is in the range minus 1 to 1, strictly in the range, and the limit does not exist if r is not in this range. If mod r is bigger than or equal to 1, the limit does not exist, and so the infinite series does not have a sum. The infinite series does not have a sum if mod r is bigger than or equal to 1. It has a sum, and the sum is a by 1 minus r when mod r is strictly less than 1. Okay. All right. So this is the first and most elementary example, and so you would say that the sum of the infinite geometric series a plus ar squared plus etc. is a by 1 minus r, correct. So now let us make a definition. Given an infinite sequence of complex numbers, we abbreviate a1 plus a2 plus etc. to sum n from 1 to infinity. This is abbreviation, standard abbreviation for infinite series, and we say that sigma n from 1 to infinity converges if the limit of the partial sums exist. The sum to n terms Sn gives you a new sequence A1, A1 plus A2, A1 plus A2 plus A3, etc. This is called the sequence of partial sums. If the sequence of partial sums has a limit, then you say that the infinite series converges, otherwise we say that the infinite series diverges, right. So, is this terminology familiar to most of you? This infinite series is probably done in a previous course, isn't it? So, let us just regard this as a review. So, we will not be proving all the theorems on infinite series, it is not possible to do it. So, we will just prove selected theorems. Thus, by this terminology, the geometric series sigma n from 1 to infinity a r to the power n minus 1 converges if mod r less than 1 and diverges if mod r is bigger than or equal to 1, correct. So, as we have just introduced two terminologies, and I use the terminology to describe the situation with the geometric series, correct. Okay, now what is the meaning of absolute convergence and conditional convergence? A series of complex numbers sigma a n is said to converge absolutely if sigma mod a n converges. That is the definition of an absolutely convergent series. You take the series of absolute values that should converge. Now, according to this definition, it is not clear that if sigma mod a n converges, then sigma a n converges. That is not clear at all from this definition. In fact, it requires proof, and the proof is, and the theorem is a non-trivial theorem because it uses a non-trivial principle. Okay. So, is the definition of absolute convergence clear? So, what we are going to prove now is absolute convergence implies convergence, in short. So, how did we do that in the last course on improper integrals? How did we prove that, and how did we prove this theorem? The corresponding theorem is also true for integrals, isn't it? What is the basic idea? You have to use the Cauchy's principle of convergence. What is Cauchy's principle of convergence? If you take a sequence a n, the sequence a n has a limit if and only if it is a Cauchy sequence. And when is it said to be a Cauchy sequence? If given any epsilon greater than 0, there is an n naught such that modulus of a n minus a m less than epsilon for all n m bigger than or equal to n naught, correct. That is a definition of a Cauchy sequence. So, you have to, what is Cauchy's principle of convergence? Cauchy's principle of convergence is that a sequence converges if and only if it is Cauchy sequence. Alright, before we get to this theorem, let us also introduce one more terminology. Suppose if sigma n from 1 to infinity a n converges, but sigma n from 1 to infinity mod a n diverges, then we say that sigma n a n from 1 to infinity is conditionally convergent, correct. Now, let us recall a few results. The first theorem and the most basic theorem is, if sigma n from 1 to infinity a n converges, then the nth term goes to 0 as n tends to infinity. This is a very easy theorem, and I am leaving out the proof because I am sure you have studied this and there is no point in doing it all over again. Do it yourself. And an important thing that we saw in the last course was that the corresponding result for improper integrals is not true. For improper integrals, we discussed the theory of convergence, right. So, what is the story there? If an improper integral converges, it is not true that the integrand goes to 0 as x goes to infinity. What was the example? Integral 0 to infinity sin of x squared dx is a convergent integral, right, but sin of x squared does not go to 0 as x goes to infinity. So, this theorem has no analog for integrals. Please remember this. Which theorems will go over from series to integrals and which theorems do not go over. One should understand that very clearly. So, now we prove the important theorem that if sigma an converges, then so does if sigma mod an converges, then so does sigma an. Absolute convergence implies convergence. Absolute convergence implies convergence. All right. So, as I said, we have to use the Cauchy's principle of convergence. So, let us say Sn is the sum to n terms a1 plus a2 plus an, and let us assume that n is bigger than or equal to m. So, let us calculate Sn minus Sm. We have to show that Sn is a Cauchy sequence. We have to show that Sn is a Cauchy sequence. So, let us calculate absolute value of Sn minus Sm. It is absolute value of, you are summing to n terms and then you are subtracting the sum to m terms, and so you are looking at the sum from m plus 1 up to n, correct? And so, this will be less than or equal to mod am plus 1 etc. plus mod an by triangle inequality. What is this? This is the sum to n terms of the series of absolute values minus sum to m terms of the series of absolute values, correct? That is exactly this. But this sequence of partial sums with absolute values thrown in will be a Cauchy sequence because it is absolutely convergent, isn't it? Sigma mod aj, j going from 1 to infinity is convergent. That means that this is a convergent sequence. That means it is a Cauchy sequence. So, given any epsilon greater than 0, there is an n naught such that mod of aj summation j from 1 to n minus summation j from 1 to m mod aj less than epsilon for n greater than or equal to m greater than or equal to n naught, correct? Because this is a Cauchy sequence. So, I apply the Cauchy's principle of convergence. Convergence implies Cauchy, that easy part of that I did. Therefore, if this minus this is less than epsilon, that means mod Sn minus Sm is less than epsilon whenever n greater than or equal to m greater than or equal to n naught, correct? Which basically means, yeah. So, what does it say? That is mod of Sn minus Sm less than epsilon whenever n greater than or equal to m greater than or equal to n naught. In other words, Sn is a Cauchy sequence. So, by Cauchy's principle of convergence, limit Sn as n tends to infinity exists. So, sigma aj, j going from 1 to infinity converges. This completes the proof that absolute convergence implies convergence. Remember, the proof heavily uses Cauchy's principle of convergence. Cauchy's principle of convergence is an essential component. You cannot prove this theorem without using completeness of some sort. You could use order completeness or Cauchy completeness. There are various proofs available, but I chose the proof using Cauchy completeness, but either order completeness of the real numbers will be used or Cauchy completeness will be used. Without using either of these completeness properties, you cannot prove the theorem. In fact, the theorem is equivalent to the completeness of real number system. Okay. All right. So, is a converse true? I mean, are there conditionally convergent series at all? Yes. Absolute convergence implies convergence. Converse is not true, right? All right. So, let us look at an example of a series that diverges. Now, let us look at a divergent series. The harmonic series is a classic example of a divergent series, a harmonic series. So, 1 plus half plus 1/3 plus etc. diverges. Okay, let us prove it by contradiction. Suppose not. Suppose it converges. Let Sn be the sum to n terms and that limit of Sn exists. If the limit exists, then it is a bounded sequence. If it is a bounded sequence, let M be a bound, pick a bound for it. That means that Sn is less than or equal to M for all n. If Sn is less than or equal to M for all n, in particular S2, S4, S8, they will all be less than M, or S2 to the power n will be less than M for all n, correct. So, let us calculate this. Let us calculate S4. What is S4? S4 is 1 plus half plus 1/3 plus 1/4. It is bigger than or equal to 1 plus half plus 1/4 plus 1/4. 1/3 has been replaced by 1/4, which is 1 plus half plus half, correct? Right? All right. Now, let us look at S8, same thing. S8 is 1 plus half plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8, greater than or equal to 1 plus half, 1/3 has been replaced by 1/4, everything else has been replaced by 1/8. So, it is bigger. So, S8 is bigger than 1 plus 3 times half, right. Same argument will go through, and S2 to the power, S sub 2 to the power n will be greater than or equal to 1 plus n by 2, which gives, but S2 to the power n is less than or equal to M. That means 1 plus n by 2 is less than or equal to M for every n. That is a contradiction. That is a contradiction. This argument is a very classic argument. We have sort of grouped the terms, right? 2 terms, and then we took 4 terms, and then we took 8 terms, and then we took 16 terms, etc. This argument can be carried out in very general terms. You can take f of n, when f is a monotone decreasing function. You can take f of n, where n is a monotone decreasing function. So, now you take a function f of n, which is monotone decreasing, and I can repeat the same argument, and one can actually come up with a test for convergence, which is called the Cauchy's condensation test. This way, please. Those who come late, please occupy those parts. Do not cut across the camera. All right. So, take a function f of n, which is monotone decreasing and positive. Do the same idea of grouping the terms, 2 terms, 4 terms, 8 terms, 16 terms, and you can prove a test for convergence, which is called the Cauchy's condensation test. It's Cauchy's condensation test. Now, let us look at this series 1 minus half plus 1/3 minus 1/4, etc. This series converges. This is a special case of a very general theorem called the alternating series test. Theorem, alternating series test. Suppose an is a sequence of non-negative real numbers and a1 greater than or equal to a2, a2 greater than or equal to a3, etc. All of them non-negative. It's monotone decreasing, then sigma n from 1 to infinity minus 1 to the power n a n converges if and only if limit of a n is 0. This is the alternating series test. All right. The proof is pretty easy, but I don't have time to do it in this course. You can look at the text of Thomas and Finney or Courant John, and you will find the proof over there. It's pretty standard. And so, with this alternating series test, it's very easy to see that 1 minus half plus 1/3 minus 1/4, etc. converges because the nth term goes to 0 and the terms are alternating in sign, correct. So, here is an example. So, now that gives us the series 1 minus half plus 1/3 minus 1/4, etc. converges conditionally. It's a conditionally convergent series because the series converges, but then the series of absolute values diverges, as we have seen just now. All right. So, here is an example of a conditionally convergent series. For the case of an improper integral, what was the example in the last course? What is the example of an improper integral which converges conditionally? You remember any of those people who were here last time? Integral 1 to infinity sin x upon x dx is conditionally convergent, right? We saw that in the last semester, in the last course, excuse me. Now, let us ask the following question: what is the significance of absolute convergence? Let us ask this question. Suppose I take an infinite series. Can the terms of an infinite series be rearranged without affecting its sum? Suppose I take an infinite series like a1 plus a2 plus a3 plus a4 etc. Let us say that this series converges to L, right. Now, I rearrange the terms. I write an a1 plus a3 and then push the a2 here, and then take the next two odd terms and then write the next even term a4, then write the next two odd terms and then write the even term next, etc. This is an example of a rearrangement. This is an example of a rearrangement. Do you think this will also have some L? What is your opinion? It will have, you expect that it will have some L. Why not? Answer is not necessarily. It is not necessary that the sum will be the same. The example is 1 minus half plus 1/3 minus 1/4 etc. is L. Let us look at the rearrangement. 1 minus half minus 1/4 plus 1/6 minus 1/8 plus 1/5. So, I write the odd term first, followed by two even terms, and then the next odd term followed by two even terms, and then the next odd term followed by two even terms, etc. Then what I have done? I have taken 1 minus half, and then there is a minus 1/4, and there is 1/3 minus 1/6, and there is minus 1/8, and there is 1/5 minus 1/10, and there is minus 1/12, and so it goes. Okay. So, but what is 1 minus half? 1 minus half is half, minus 1/4, 1/3 minus 1/6 is 1/6, minus 1/8, etc. This is exactly half of 1 minus half plus 1/3 minus 1/4, etc., which is L by 2. Original thing was L. This rearrangement converges to L by 2. Of course, you say that this does not prove anything. Maybe L is 0, perhaps. Perhaps L could be 0. Then this does not prove anything. L is equal to L by 2 if L is 0, no problem. How do you know that L is not 0? It is not difficult to show that L is positive. If you look at the proof of the alternating series test, if you study the proof of the alternating series test, you will immediately be able to see that the sum is positive. In fact, later on we will actually calculate the sum, and we shall see that the L is actually log 2. The L is actually log 2, natural log 2. So, it is positive, and so this is false. So, the rearrangement does change the value of a infinite series. So, the answer is that you cannot rearrange the terms of an infinite series, because by doing so you will be tampering with the sum of the infinite series. Is it clear? Now, perhaps you are more bewildered by this example. So, the point is, it is not very difficult to understand why this is happening. Let us suppose, let us try to understand why. I make a following statement. I say that when you rearrange the terms of an infinite series, expect the value to change. The fact that the rearrangement alters the sum of an infinite series is to be expected. What is remarkable is that when it is absolutely convergent, rearrangement does not affect the sum. That is remarkable. The fact that rearrangements change the value of the sum of an infinite series is not at all remarkable, and let me convince you why that is not remarkable. Let us take two infinite series 1 and 2, a1 plus a2 plus a3 plus a4 plus a5 plus a6 etc. Now I am writing a1 plus a2 first two terms, and then I write an a4, then I wrote an a3 plus a6, and then I wrote so it's a a1, then 2 and a 4, and then the a3, and then the 6 and the 8 etc. The odd term I wrote first, and then followed by two even terms, next odd terms, and then couple of even terms etc. I just taken one particular rearrangement, right? The next one will be a5, the next odd term will come etc. That is one rearrangement. Now let us write down the partial sums for the two infinite series. The partial sums for 1 and 2. Let me display it here. The partial sums for 1 are a1, a1 plus a2, a1 plus a2 plus a3, a1 plus a2 plus a3 plus a4 etc. The partial sums for 2 is a1, a1 plus a2, a1 plus a2 plus a4, a1 plus a2 plus a3 plus a1 plus a2 plus a4 plus a3, a1 plus a2 plus a4 plus a3 plus a6 etc. So the partial sums for the two series have been displayed. Now notice that a1 plus a2 plus a3 is a term of this sequence. It is not going to appear in the second column. Likewise, the term a1 plus a2 plus a4 is not going to appear anywhere in the first column. This term a1 plus a2 plus a3 plus a4 plus a5 is not going to appear anywhere in this column. a1 plus a2 plus a4 plus a3 plus a6 is not going to appear anywhere in the left column. What has happened? The sequence of partial sums is completely different for the two infinite series. Therefore, it is not surprising that their limits are different. What has happened is, by rearranging the terms of an infinite series, if you rearrange the terms of an infinite series and write down the sequence of partial sums, the sequence of partial sums are entirely different. So it is no surprise that a rearrangement alters the sum of a series. This is something that you have to tell your students. They will ask you, they will be puzzled by this. You have to display them an example, and you will have to convince them why is it not surprising. It is not at all surprising that when I rearranged 1 minus half plus 1/3 minus 1/4 in that way, I got half the result. I got L by 2. It is not surprising at all. Correct? So the partial sums, okay, so whatever I just said has been summarized in the slide. The partial sums of the two series are different, and so it is not surprising that rearrangements alter the sum of an infinite series. What is surprising is the theorem of Dirichlet, that if sigma an converges absolutely to L, then every rearrangement of the series converges to the same value L. That if a series is absolutely convergent, then no matter how you rearrange it, the sum does not change. This theorem was proved by Dirichlet. We will not prove this theorem. Again, it is not difficult to prove. I mean, you will. I could have an entire course on infinite series, and then we could prove all these theorems. It is not difficult, but there is simply no time, and we will not prove this theorem. So, this is the theorem of Dirichlet. What is the story with a conditionally convergent series? In stark contrast, we have the following remarkable theorem of Riemann. If you have an infinite series which converges conditionally, then given any real number alpha, I can find a rearrangement which converges to alpha. No matter what alpha you give me, I can always find a rearrangement for which the series will converge to alpha. This is called the Riemann's rearrangement theorem. In fact, much more is true. The theorem has not been stated in utmost generality. What is true is that Give me two real numbers alpha and beta, say alpha less than beta, then I can find a rearrangement whose sequence of partial sums keep oscillating between alpha and beta. The upper limit will be alpha and lower limit will be beta, like that. I can always make the series oscillate between any two pre-assigned numbers. That also is possible. I can find a rearrangement that will make it converge to plus infinity. I can find a rearrangement that will make it converge to minus infinity. This is a series of real numbers. Huh? If ANs are real numbers, series of, in this particular theorem, I am assuming that the ANs are real, okay? Sequence of real numbers. I have taken a sequence of real numbers and it's a real series. Story is very different from complex series. We are not interested in that. Just a sample theorem that it's rather spectacular that when the series converges conditionally, rearrangements can do anything. Now, here is a little exercise for you. Use the Cauchy's principle of convergence to prove the following theorem. If you take two sequences of real numbers, 0 less than or equal to an less than bn for all n bigger than or equal to n naught, then the dominate so that means the sequence bn dominates the sequence an. The sequence bn dominates the sequence an. So, sigma bn converges implies sigma an converges, right. This is called the comparison test, and we shall use the comparison test very soon in other theorems. So, please try to prove this. It is a simple application of Cauchy's principle of convergence. We have proved the comparison test for improper integrals in MA 108. The same proof, pretty much the same proof goes through. Integrals get replaced by sums. It is just a direct consequence of Cauchy's principle of convergence. All right. Okay. Any questions so far on what is going on? Everything clear? The concept of convergence, absolute convergence, conditionally convergence, absolute convergence implies convergence, rearrangements, absolute convergence, when you have absolute convergence, rearrangements do not affect the sum, whereas the series is conditionally convergent, then you are not allowed to rearrange the terms of an infinite series. Okay. Now, let us look at a few tests for convergence. The most basic test for convergence is the ratio test and the root test. The ratio test, suppose sigma an is a series of non-zero complex numbers such that limit as n tends to infinity mod an plus 1 upon an equals L, right. I am assuming that the limit exists, either it is a finite number or it is plus infinity. The limit either exists as a finite real number or this mod an plus 1 upon mod an goes to plus infinity. It's what does it mean to say that a sequence Bn goes to plus infinity? It has a very precise meaning. You know what it is. So, that is what I mean here, that is the limit is L as a real number or as plus or it is plus infinity. Then three cases rather, sigma an converges absolutely if L is less than 1, strictly less than 1, mind you. Sigma an diverges if L is bigger than 1 or if L is plus infinity. The third case is if L equal to 1, the test fails, no conclusions if case L is 1. This is the ratio test, correct. Let us get to the proof of the ratio test. So, let us take case 1, that is L is less than 1. L is less than 1, so let epsilon greater than 0 such that L plus epsilon is still less than 1. You have 1 and you have L, add a little something to L, so that it is still less than epsilon. it is still less than 1, excuse me, correct, I can always do that. Then for this epsilon and this limit exists, so there will be a corresponding n naught. I am going to invoke the definition of limit. The limit of something exists and that limit is less than 1 and I picked a certain epsilon greater than 0. For this epsilon there will be a certain n naught. So there exists an n naught such that mod an plus 1 upon an minus L less than epsilon for all n bigger than or equal to n naught, correct. That means L minus epsilon less than mod an plus 1 upon an less than L plus epsilon. We are really not interested in this part at all. Let us just focus on this part for n equal to n naught plus 1, n naught plus 2, etc. Multiply, so let n run from n naught plus 1, etc. up to n minus 1. So I am taking, instead of n I am taking k. So I am multiplying out, I write down this inequality for n naught plus 1, n naught plus 2 up to n and multiply out the inequalities, correct. What are you going to get? Product k from n naught to n minus 1 mod of ak plus 1 upon ak less than L plus epsilon to the power n minus n naught. Now what is this product? It is a telescoping product, right? Things will cancel out when you write it down. You are going to get mod an less than mod an naught and this L plus epsilon to the power n upon L plus epsilon to the power n naught. As far as I am concerned, this is a constant, not depending on n, and here is a power of a constant, correct. So an is less than this whole thing, let us call it bn. Let us call this whole business bn, right. What is sigma bn now? That is a constant. So what is sigma bn? Sigma bn is a geometric series. Sigma bn is a geometric series with common ratio L plus epsilon, which is less than 1. So sigma bn will converge, and so by comparison test sigma mod an will converge. In other words, sigma an converges absolutely. That completes the argument for the first case, alright. So that is all I have written down. So sigma an converges absolutely. The other cases I am leaving it as an exercise for you. There are 3. The third case there is nothing to do. Third case simply say the test fails. We abandon the test and no conclusions are drawn. The second case, when L is bigger than 1, I am leaving it to you for analysis, okay. Alright. This is D'Alembert's ratio test. What is another test that is very similar to D'Alembert's ratio test? The Cauchy's root test, alright, that is the next one. Cauchy's root test. Suppose an is a sequence of complex numbers such that limit as n tends to infinity mod an to the power 1 over n equals L. Either the limit exists as a real number or it is plus infinity. Then item number 1, sigma an converges absolutely if L is less than 1, sigma an diverges if L is bigger than 1 or if L is infinity. Test fails if L equal to 1. Remember here when I say L is plus infinity, I mean the limit of this is infinity, okay. It is not just enough that some subsequence goes to infinity, that is not what I mean. I hope you understand what this L equal to infinity means. When is a sequence Bn set to converge to infinity? If given any real number R, there exists an n naught such that Bn is bigger than R for all n bigger than or equal to n naught. That is, it properly goes to infinity. It is not just enough that some the odd number terms go to infinity and the even number terms go to 0. That is not the meaning of saying that the limit is infinity. Limit is infinity means what I just spelt out. Okay. So, when I say L may be infinity, that is what I mean. Given any real number R, all these things exceed R for n bigger than or equal to n naught. Okay. For all n bigger than or equal to n naught, not just for infinitely many values. Proof is similar to the proof of the ratio test. We will not be discussing the proof here, correct. Is it clear? You are familiar with ratio test and root test and everything, alright. So, now let us look at a few examples on how to use the ratio test and root test. Examples. So, let Z be an arbitrary complex number. Consider the series sigma n from 0 to infinity z to the power n upon n factorial. We apply the ratio test. What is a n? A n is z to the power n upon n. If z is 0, the result is trivial. If z is 0, the result is absolutely trivial. So, I may as well assume that z is not equal to 0. Okay. So, look at a n plus 1 upon a n. What is a n plus 1 upon n mod? It is mod z upon n plus 1, and what is the limit of this as n tends to infinity? 0. So, the L that appears in the ratio test is 0, and 0 is less than 1 surely, and so by ratio test the series converges absolutely. The series converges absolutely for all values of z, correct. Next example, sigma n from 1 to infinity z to the power 2n minus 1 upon 2n minus 1 factorial, and sigma n from 0 to infinity z to the power 2n upon 2n factorial. What is your a n in the first case? A n in the first case is z to the power 2n minus 1 upon 2n minus 1 factorial, correct. And so, a n plus 1 upon a n mod is what? Mod z squared upon 2n plus 1 into 2n, correct. What is the limit of this as n tends to infinity? 0. So, the L that appears in the ratio test is 0. The L that appears in the ratio test is 0, and so the series converges absolutely for all values of z, correct. Same is the case with this series, right. Clear? Third example is sigma z to the power n. Sigma z to the power n. It is very easy to see that this converges absolutely when mod z is less than 1, and it diverges when mod z is bigger than or equal to 1. Direct application of root test. Root test will give you divergence when mod z is strictly bigger than 1. When mod z is equal to 1, the nth term does not go to 0. That is the reason. Root test will give you divergence for mod z strictly greater than 1. But when mod z is equal to 1, you cannot apply the root test, but then you have to look at the nth term. The nth term does not go to 0, and that is why it diverges. Next is the case sigma n from 1 to infinity z to the power n upon n squared. The series converges absolutely when mod z is less than 1, diverges when mod z is bigger than 1. This will follow immediately from the ratio test. What happens when mod z equal to 1? Ratio test will fail, root test will fail. I will leave it to you to discuss this as an exercise. We can come back to it during the tutorial class. Next, consider the series sigma n from 1 to infinity n to the power n into z to the power n. Straightforward application of root test. It will tell you that the series will converge when z is 0, and it will diverge when z is not 0, because what is a n? A n is n to the power n, z to the power n. So, what is mod a n to the power 1 over n? N times mod z, n times mod z, and the limit exists if mod z is 0, and then the series converges. If mod z is not 0, that limit is plus infinity. The limit exists, but it is plus infinity. and so it again diverges. Here are some exercises, please write them down. Discuss the convergence of sigma n from 1 to infinity 1 plus 1 over n to the power n squared into z minus 5 raised to the power n, sigma n from 2 to infinity 1 minus 1 over n to the power n squared into z squared plus 1 to the power n, sigma n from 3 to infinity z to the power n upon log n. Fourth one is sigma n from 1 to infinity z to the power n squared, and fifth one is sigma n from 1 to infinity z minus 1 to the power n squared upon 2 to the, use ratio test and root test. These are all exercises on ratio test, root test. Now let us come to the main topic of this chapter, power series. So power series, the series of the form sigma n from 0 to infinity a n z minus c to the power n. Such an object is called a power series. A n is a given sequence of complex numbers and the coefficient sequence, and the complex number c is the center of the power series, and z is a variable that is allowed to take complex values. So you want to understand all these examples that we have discussed so far, we have seen for what values of z does it converge. The power series like sigma z to the power n upon n factorial, that was the very first example. Series converges absolutely for all values of z. Sigma z to the power n, series converges absolutely for mod z less than 1 and diverges when mod z is bigger or equal to 1. Sigma n to the power n into z to the power n, series converges when z is 0 and diverges otherwise. So we have seen examples of, the examples that we have seen so far are examples of power series, they are deliberately chosen examples. So now more generally this is the way the power series will look like. You have sigma n from 0 to infinity a n z minus c to the power n, right. So now you know, so the c is called the center, a n's are the coefficient sequences, and z is a complex variable that will appear in the power series. It is a simple example of a series of functions. Sigma fnz, take a series of functions, sequence of functions fnz, and you construct the infinite series, each term of which is a function of z, right. In your PDE class you will see Fourier series, sigma a n cos nx plus b n sin nx, that is also a series of functions, but these functions are not, it is not a power series, it is an example of a Fourier series. So now you see examples where you have a series, infinite series, where every term of the infinite series is a function. But the simplest function is a monomial, right? A n z to the power n. So a power series is simply a series of functions whose summands are all monomials, a n z to the power n. So we have seen examples. So these are 3 examples of functions z to the power n upon n factorial, sigma z to the power n, and sigma n to the power n z to the power n. So for the first one, the series converges for all values of z, converges absolutely for all values of z. For the case, second case, the series converges absolutely inside the unit circle and diverges outside. Third case is the series converges only at the center, namely z equal to 0. This is a very typical situation with power series. In fact, given any power series, exactly one of the following is true, that the series converges absolutely on the whole plane, or the series converges absolutely in the interior of a disk and diverges outside the disk, the closed disk, that is it converges absolutely in when mod z minus c is less than r, and it diverges when mod z minus c is strictly bigger than r. The third case is that the thing converges only when z equal to c, only at the center. When z equal to c, every term is 0 except the constant term, it converges trivially. The power series will converge always when z equal to c, but that may be the only value for which it converges. We have seen an example. Sigma n to the power n into z to the power n. That is an example of a power series which converges only when z equal to 0. The third case can happen. The power series may converge only at the center and nowhere else. Uninteresting case. The power series converges in the whole plane. Interesting. Power series converges in the interior of a unit disk. On the circle, we have no clue as to what is happening. Outside the circle, it diverges. Okay. So, exactly one of these three things will hold. That is the domain, in other words, the domain of absolute convergence. That is the open set. Remember, domains are open sets. The largest open set on which the power series converges is either empty, if the power series converges only at the origin, only at the center and nowhere else, then the open set on which the power series converges is empty. That single point, no, it has no, it doesn't, it's not an open set. The single point is not an open set. Or it could be the whole plane. The whole plane is an open set. Or it could be the interior of a disk, and any larger open set, it will not converge absolutely. Open sets, we are talking about open sets. So, here is a theorem. Suppose that the power series sigma n from 0 to infinity a n z minus c to the power n converges when z equal to z naught, and z naught is not the center, then it converges absolutely in the disk mod z minus c strictly less than mod of z naught minus c. This is a preparatory theorem for the main result. What I described before this slide was the main result describing the region of convergence of a power series, the domain of absolute convergence of a power series. The largest open set on which a power series converges is a disk, and that radius of that disk is called the radius of convergence. Before we get to this, we need a preparatory theorem. This is a preparatory theorem. So, suppose you have a power series that converges at a point z naught other than the center. Then draw a circle through z naught with center at C, and inside this circle the power series will converge absolutely. Okay. Since the power series converges when z equal to z naught, sigma n from 0 to infinity a n z naught minus c to the power n converges to begin with. If it converges, the nth term must go to 0, and if the nth term goes to 0, in particular it should be a bounded sequence, absolutely. Yeah. So, in particular the nth term goes to 0, therefore, the sequence is a bounded sequence. So, there is an m such that a n z naught minus c to the power n less than m for all n, right. So, now the trick is take the term of the power series with the absolute value thrown in, multiply and divide by this z naught minus c to the power n, alright, multiply and divide by z naught minus c to the power n. This business here is less than m. What are we left with? We are left with the power. So, the terms in absolute value are dominated by a terms of a geometric series, and this geometric series will converge as soon as mod z minus c is strictly less than mod z naught minus c. So, the geometric series sigma n from 0 to infinity m mod z minus c upon z naught minus c to the power n converges if and only if mod z minus c upon mod z naught minus c is less than 1. So, the dominating series converges when mod z minus c is strictly less than mod z naught minus c. So, by comparison test, the power series converges absolutely if mod z minus c is less than mod z naught minus c, and the proof is complete. Is the proof clear? The theorem clear? Statement of the theorem clear? So, what does the theorem say again? So, what is the statement of the theorem? You have a power series with center C, and the power series converges at a point Z0 other than C. Draw the circle through Z0 with center at C. Inside this circle, the power series will converge absolutely. So, the moment the power series converges at least one more point other than the center, then you immediately have a nice disk of absolute convergence, correct? You have a nice disk of absolute convergence, is that right? So, now what happens is that, let us take the three possibilities. What are the three possibilities? The power series converges absolutely everywhere. The power series converges only at Z equal to C. Third thing is that there is the largest open disk centered at C on which the power series converges absolutely. These are the three possibilities, and these three possibilities are mutually exclusive. Only one of them can hold, correct? By by the very nature of these three statements. We have to prove this now. How do we prove this? Case 1, if the power series converges everywhere, there is nothing to prove, then item number 1 holds. Case 3, if the power series converges only at C and at nowhere else, then there is nothing more to prove. So, suppose that 1 and 3 are false. Suppose that the power series does not converge everywhere. Suppose that there is a point other than the center at which the power series converges. Then you have a open disk on which the power series converges absolutely. Now, take the union of all open disks, take the union of all open disks centered at C on which the power series converges absolutely. I repeat, I am taking open disks. Take the union of all disks which are open, right, centered at the C, centered at the point C, and on each of these disks the power series is supposed to converge absolutely, and take the union of all these disks. It can't be the whole of C because the power series does not converge everywhere. There is at least one point where the power series does not converge. So, union of all these disks cannot contain that particular point. So, it can't be the whole of C. It can't simply be the point also. So, what is the union of all these disks? It is going to be an open disks, because you are taking open disks. So, the union is also an open set, and you are taking concentric circles, concentric disks. So, union is again going to be a disk. That disk, let us say, has radius r. Inside on that disk the power series converges absolutely by construction. Suppose I take a point which is outside, suppose I take mod z minus c bigger than r. Suppose I take, you have this disk, right? I take a point which is outside the disk, not on the boundary, outside. Can the power series converges on that at that point? No, because if it converges on that disk, then I can draw the circle, and that circle will contain this disk properly inside. That means that this disk that we have, that means I can find a disk of larger radius. I can find an open disk of larger radius on which the power series converges absolutely. That is a contradiction, because we had taken the union of all disks, right, and that is how we got the disk of radius r. That is the argument. Okay. So, the theorem, given a power series sigma n from 0 to infinity a n z minus c to the power n, precisely one of the following holds. The series converges only when z equal to c. There exists r bigger than 0 such that the series converges absolutely on the disk mod z minus c less than r and diverges on mod z minus c bigger than r. The series converges absolutely on the whole of C. These three cases are the three cases are mutually exclusive. So, assume that 1 and 3 fail, that means that it converges at a point other than C and it does not converge everywhere. Then we will prove the 2, the middle case 2. So, there exists a point Z naught other than C such that the series converges when Z equal to Z naught. So, the series converges absolutely on the disk delta naught, which is Z such that mod Z minus C strictly less than mod Z naught minus C. So, delta naught is a non-empty open disk, correct, on which the power series converges absolutely, and take omega to be the union of all, take omega to be the union of all disks centered at C such that on each of these disks the power series converges absolutely. Then omega is non-empty because it already contains delta naught. Omega is not equal to C since the third case has been ruled out. Now, what is the third case? The power series converges for all values of C. We are ruling out that case also. So, omega cannot be the whole C. So, omega being a union of concentric disks is again a disk because it is not the whole of C. So, let us call omega to be this disk Z such that mod Z minus C less than R. Then the power series converges on omega. Okay. Now, what are we supposed to show? We are supposed to show that, now we have to show that the power series diverges on the complementary open, the open set complementary to this. That is, it on the S with a set of all Z such that mod Z minus C is bigger than R. On this set, the power series must diverge. Suppose not, suppose there were a point Z prime at which the power series converges. Then by the previous theorem, it converges on this disk Z such that mod Z minus C less than mod Z prime minus C. So, this disk is contained in omega because omega is the union of all open disks on which the power series converges. But then mod Z prime minus C is bigger than R, correct. So, this cannot be contained in omega because omega is the union of all disks, right, because omega, what is the radius of omega? R, correct. So, and this number is bigger than R. So, this disk cannot be contained in omega, contradiction, finished, the proof is complete, correct. Is it clear? Argument is clear. The geometry of the domain of convergence of a power series, one of the most important theorems. It is a beautiful result on power series in one variable. If you take a power series in two variables, it is not true. Suppose I take sigma aij z to the power I w to the power j. I take a power series in two variables. The domain of convergence of a power series in two variables is quite complicated. Let us look at a simple example. Look at sigma z into w to the power n, geometric series. It will converge when, precisely when mod zw is less than 1. Suppose I take z and w to be real. What is this region mod zw less than 1? It is the region inside the four branches of the hyperbola, not asteroid, xy less than 1, hyperbolas, that region inside the hyperbola. So, the geometry is much more complicated, correct. The last slide of today's lecture, this is lecture number 3. The positive number R of the previous theorem is called the radius of convergence of the power series. In the previous, we just saw that there is a largest open disk on which the power series converges. The radius of this disk is called the radius of convergence of power series. If the power series converges everywhere, then we say that the radius of convergence is plus infinity. If the power series only converges in the center and nowhere else, then we will say that the power series has 0 radius of convergence. Okay. So, the notion of radius of convergence of a power series has now been finally established. There is a formula for the radius of convergence of a power series in terms of the coefficients it is called the Cauchy-Hadamard formula. You will find this formula in all the textbooks. It says 1 over R is lim sup of nth root of mod an. We will not derive this formula. I will not tell you what is the lim sup and stuff like that. We won't need this formula for our work. If at all we need it, at that time we shall look into it. I don't think I'll need that formula for this course. So there's a formula for the radius of convergence also. So you will find that in most books. That formula is exceedingly important for theory, but in several examples you cannot apply the formula, because take the simplest example, z to the power n upon n factorial. How will you understand the nth root of n factorial? You have to use the Stirling's approximation formula. So already the Cauchy-Hadamard formula becomes unwieldy in the simplest of the example. Whereas a direct application of ratio test will give you the radius of convergence. The ratio test tells you that the series converges for all values of z, right? So you don't need to apply the Cauchy-Hadamard formula every time, all right? So I'll close this lecture here and we'll meet in the afternoon. I'll lecture in the afternoon also. That will be the 4th lecture, okay?